Hello, welcome to my digital presentation on technology transitions of lighting. My name is Alan Proctor. I'm a junior at Arizona State University. This is for my CE 300 business practice course, and we're going to try to answer the question, how should ASU illuminate campus? The objective, reduce energy output while maintaining light quality and intensity. The intended audience is for ASU in general. This is a macro analysis, and the method to obtain the solutions, we're allowed to use net present value calculations and the use of cash flow diagrams. Now, before we get started, I wanted to show this picture. If this was going to come up, I took this picture on the weekend when this building was locked, and here we go. This reads, APS in partnership with APS Energy Services has implemented an energy conservation program to retrofit lighting, motors, and control equipment in this building to help us use energy wisely and help protect the environment, blah, blah, blah. Yes, that fascinated me because that means maybe somebody will be paying attention to this video. Okay, we will get to the answer, and there is no easy way to get to this answer, but try my best. How should ASU illuminate campus? What are our applications, indoors or outdoors? If we're looking at outdoors, we see high intensity discharges, compact fluorescent lighting, light emitting diodes. Inside these high intensity discharges, which are used for parking lots and large like stadiums or gymnasiums. If you see a blue light and the blue hue, that is a metal halide. If you see an orange, that's a high pressure sodium. But we are not interested in those because they are very old technology, as well as the incandescent, and not very energy efficient, although high intensity discharges are slightly more energy efficient than even compact fluorescence. When you could see here in this chart of light output, 2800 lumens of light output requires only 47 watts of light for the high intensity discharges, where it requires 55 for the CFLs and only 28 for the LEDs and 150 for incandescents, which is obviously why we don't care about them. Now, we can use the sun as well, which we will be considering in our third and fourth option to retrofit daylighting in the buildings and use LEDs as a supplement or CFLs as a supplemental lighting. Option 1 is basically our control. This is what we're doing now. Not much daylighting, and we're using a lot of CFLs. And option 2 would be just switch it and do all LEDs. Here's a couple equations that I use to calculate this. Not that one, because that would be for future value, and we're assuming the future value to be 0. And so we use this as a reoccurring payment formula. This number, this will give a discount factor, essentially tell us how much is that future money worth to us now, and we're going to have to use some assumptions to get to that. The next page I'll show the assumptions, and this is the formula we use to calculate everything. Net present value equals initial payment minus the reoccurring payment, the sum of reoccurring payments. And the net present cost is just inverse to the net present value, and that is all that was saying. Here are the assumptions. Sample building in this analysis uses 1,000 light bulbs are under review, and each light bulb is expected to put out 2,800 lumens of light output. Times that 2,800 by 1,000 and you get that K. So per sample building you got 2,800,000 lumens of light output, and in words we have the CFLs consuming 55 watts of energy to produce 2,800 lumens of light, where LEDs only consume 28 to produce the same, and that is why they are slightly more energy quite a bit more energy efficient. We'll see how that plays out in the long term. And the hours of use per decade, now you might say 50,000 hours, that's pretty convenient, isn't it? But hey, looky here. I've done this 10 years times 365 days a year times how many hours? Not 24, we're going to be somewhere, well, let's go 13.7-ish. See where that, oh, that is good. That's close. 13.7 hours is close enough to the hours of use per day. So we will use 50,000 hours as the hours of use per decade. However, if there is daylight in the building, we're going to cut that number in half. And here is the assumed discount rate of 15%, because this is our money. We're college students. We can use this for a lot of other things we probably rather would. That's why we're choosing such a high discount rate. Now, to go through each cost analysis, we start by drawing cash flows, or the fund figures. This is for what we have right now. We have no initial investment to start what we have now, but this is the cost to maintain for each decade. As you can see, this adds up quickly, seeing as how the net present cost is $4 million. Okay, so what if we just switch to LEDs? That would cost approximately $35 a light times 1,000 light bulbs, $35K, and we're changing this instead of 55 to 28, which is great because now we're saving money over time. And this may look a little weird to you. This is 8 cents per kilowatt hour. I just divided that by 1,000 to get that divided by watts per hour, so the watts and the hours canceled nicely. And at the end of the net present cost calculation, we're looking at about 2.5 million to do this, and so that is substantially cheaper than what we're doing now with majority of compact fluorescents. Now, what if we were to incorporate daylighting into our building? This is what it would look like. Many assumptions had to be made for that, but $250,000 was selected. It shouldn't be too expensive to retrofit a building with daylighting. Mainly we're looking at changing regular windows to smart windows that can adjust for heat differential, that could increase the temperature and kick on the AC too early. The tint of the window can change to make sure that this is optimized in a very complex and awesome control system that we should use, seeing as how ASU is all about it. We can have sensors on everything, and this will have a small cost to maintain, and we're going to assume negligible for now. And so going through this calculation, we get our net present cost of $1.5 million, which is a whole $2.5 million cheaper than what we're doing now, and a whole $1 million cheaper than if we chose not to retrofit daylight into into a select sample building. Now, option 4 looks at using CFLs with daylighting. Now, you may have seen what this answer comes to. As you see, a slightly lower initial cost because we don't need to replace any bulbs. The CFLs are already there, so we're going to have a slightly lower cost to start up and a slightly higher cost to maintain, which will give us a ending net present cost of $2 million. So, in conclusion, the answer is this. Option 3, to retrofit daylighting with the use of supplemental LEDs attached to smart technology to use the best optimized amount of daylighting in combination with LEDs. This is why LEDs, not CFLs. They light up instant where CFLs don't. They're durable, less heat, They're not affected by temperature and humidity, and they don't have mercury, 5 milligrams of mercury per bulb, requiring special ways to dispose of this. So again, ASU, here it is. I give you the